Hey folks, in this video, let's do an overall evaluation of the performance between arrays and lists. So we already know what arrays are, right? We've used them a lot. You guys have seen them a lot in other courses. Lists, we just kind of reconceptualize right now to make sure we're on the same page. How do I know when to use one or the other? Right? That is the question of the day, right? How do I know? So they're both kind of legit ways to store data, right? My overall problem is that I have a bunch of things, right? I maybe have a bunch of numbers, a bunch of strings. I need to store them somewhere. And I have my choice. Do I use an array? Do I use a list? Both of these are containers I can use to store stuff. So how do I know when to use which one? Let's start by drawing them out. How do they look in memory? So this is system memory. I have a nice cloud here, right? That's the best icon I could come up with. This is basically your RAM, your main memory. Okay, that's what this is. So I have my RAM memory here. I have my array, right? This is my left-hand side is my array, my int data, right? This is maybe what we started with the array initially, right? Here I have things stored contiguously. What that means is they're stored back to back. So this picture here has 2 next to 4, next to 6, next to 8, next to 10. All those things are back to back. Those are contiguously stored, okay? So that's one thought. So that's actually kind of nice though, because if I want to read something, it's relatively straightforward. It's easy for me basically to jump to any of these, right? So if I want to read from 2, right, I can go and do data of 2. If I want to do data of 0, if I want that first element. If I want the number 8, I can do data of 3. Data of 3. Okay, so that'll lead me over here. That'll lead me over here. Pretty easy to get anything, okay? The other one idea we've just introduced is that of stacks. Is that of lists. So for a list, we don't really have kind of this immediate access. Things are stored non-contiguously. So notice in my picture here, I have my little numbers, but rather than being back to back, they're just all over the place, right? They're in different places in system memory. So this is kind of a little bit hard to work with. It's easier for me to get to the first element in there, which we typically call the head, right? It's easier for me to get that number 2. But if I want to go and get the number 8, I can't just jump to it directly. I need to follow links. So I need to go from here to here to here to here, right? I need to follow different links in a chain, right? And this is kind of a fundamental difference, right? So the memory is non-contiguous, and that implies I need to take these little steps to get from one place to another, okay? So that's my basic idea, right, of how I'm storing my arrays and lists in memory, right? Because that's what impacts me, right? So when I'm trying to access this, when I'm trying to read data, write data, add data, change data in any sense, right? What matters is how it's laid out in main memory, right? Depending on how it's laid out in main memory, that's going to impact how my different operations will perform on using this structure or this other structure, right? That's what we care about. Okay, so let's take a look at some specific examples and try to figure out when we want to use one over the other. So first of all, looping over, okay, we have a bunch of operations, so I have 5 of them here, just as samples. First one, looping over each value and printing it out. So this is the traversal operation. I've been recording here for like 2 hours, guys, so my pronunciation is going a little bit off. You don't know what it's like to be here in front of these lights for 2 hours. Anyways, the traversal operation, the first one we're going to look at. So traversal. How do we do traversal? So traversal basically is that problem of I want to loop over every element one at a time and print out each of them, right, in succession. Well, for an array, that's pretty easy. I can use a for loop. I can go one at a time, right? So I have a for loop that basically has like an I as an index, and it goes from 0 up until 4, right? And it'll basically walk along, and you'll do data of each of these. Data of 0, data of 1, data of 2, data of 3, data of 4, and you print out each of them, right? Pretty easy. For a list, you'd have basically a while loop, right? And this while loop would have basically this conditional that says like, look at the node. If the node isn't empty, keep on looking at it, right? And you would have basically a while loop that goes and touches each node in sequence, right? And a loop over each of them. And each time basically has to update itself to basically like, look at the next node, look at the next node, look at the next node. It's kind of like you can visualize that you have like an arrow here, and then you have to update it to be over here, then over here, then over here, then over here, right? You have nodes, you have this little arrow, this little iterator item or iterator variable that basically has to go and look at each of those different nodes. And so it takes you actually a little bit more work to get to a specific one. Now, for the case of a traversal, you just want to list out everything that's there. That's actually going to be the same, right? So whether I have to basically use an array or a list, I'm basically going to touch every element in order. So it's going to be the same performance. It'll be big O of n performance. I need to look at all n elements, okay? Hopefully that makes sense, right? I have to look at n elements, so it's going to cost me O of n for both of them. Doesn't matter how I get to them, I'm going to have to look at n of them at the end of the day. All right, printing out the third element, so the selection problem. Printing out the third element, let's see. For an array, can you guys tell me or try to guess, what is the big O of it for an array? Well, for an array, it's constant time. Just data of whatever, right? Data of 3 gets me there instantly. What about for the list? A little bit more work, right? you have to go one at a time and go through these different elements, right? So in general, we'd say for selection, right, to select an element in general, it's going to be cost O of 1 in the array. It's going to be cost O of n in the linked list because you got to navigate to the right position to be at. So here we want to use an array, right? And it'll be O of n, O of 1, excuse me. All right, next one, binary search to check to see that 8 is in the data. That's a search problem, right? We're jumping back and forth. For an array or a list, what do we want to use? Well, I'll ask you guys, what will be the performance for a list? Big O. Any guesses? Big O would look a little bit like O of n, because again, we got to jump around and look at the different positions. We got to jump back and forth, and we can't do it directly. We have to move back and forth. So that'll be a little expensive. For an array, it'll be O of 1. So an array wins here as well. This is O of 1. All right, adding number 7 between number 6 and 7, the insert problem. This is a little bit more tricky. For an array, it's going to be O of 1, right? We already talked about the resize problem, right, for an array, right? That's going to be O of n for an array. For a list, here it depends a little bit. So if I actually already have a reference to 6, I can add something instantly, right? It should be between 6 and 8. But I can add something instantly, right? If I have a node in my, a reference to something here, right, I can add a node by it instantly, right? Because in my picture, right, I can basically do this. I can change the links to have another value in there, right? That's pretty easy. Here, the problem is that my array, I can only add it in one space, and sometimes that space isn't available. That's why I have to create an entirely new array instead. I can't just expand the one that I have. But over for a list, because a list is broken into little pieces, those little pieces can go wherever, and so I don't have that trouble, right? I can just add them in, rearrange the links. So for a list, right, it's going to be a better option, right? So a list, right, will be, depending on whether we have a reference to 6 or not, a list will be either O of 1 or O of n. All right, last one here, removing the number 4. We want to delete the number 4. What will be better? In this case, well, the array, same thing, resize issue. List, it's going to be basically constant time, right? Again, it's a rearrange the arrows thing, right? I don't have to change much. So over here, list will be the cheaper one. And I guess I can write in, it's O of 1, right, if I have the reference to right where I want to delete, or O of n if I need to go search for it first. All right, so that's kind of my little, some of my ideas there, right? So these are some different scenarios. Try to think about it a little bit, maybe relate them to how the memory location works, right? And kind of get that sense of, this kind of is nice because everything's together, right? So I can actually kind of jump wherever instantly. I just need to do some math to jump to one from another. Whereas over here, these are links. I only know about my neighbor, so I need to go talk to a bunch of people before I can get to where I'm going. So try to think about that a little bit intuitively and see if you can kind of match these choices of using an array versus a list for these different ones, or of course the case where it's the same. All right, so that's about it for this video. Hopefully you guys have at least some sense, right, of when you'd want to use one of these structures over another. In the next set of videos, we're going to start using that idea of a list to actually implement a stack.